I'm Emily, and today we're going to be going over vectors together. The important thing to know with vectors is that they only have a direction and a length. That means, say here, I draw a vector. Let's make a nice little coordinate axis. So you have the vector 1, 2. Let's make this be the x, up here be the y. And so we're going to have a nice little vector like that. The thing with vectors to know is that they only have a magnitude and a direction. They do not have a position. So if I were to draw the same vector, let's say up here, it'd still be considered the exact same vector because it's just like moved upward. Now, of course, if you rotate a vector, now it has a different direction, therefore it's a different vector. And if you make a vector a lot longer, it's now a new vector because it's a lot longer. And to find the length of a vector, which is something you're going to have to do in your worksheet later today, is since it's at an angle, I like to make a triangle with it. And then since this is a right triangle, can you guess what we're going to use? That's right, Pythagorean theorem. So the length of the vector, otherwise known as the magnitude, is just Pythagorean theorem. So we're going to have 1 squared plus 2 squared is equal to the square root of 5. And a way to denote the magnitude is sometimes you'll see absolute value signs. So let's call this vector up here v1. So you'll see like absolute value of v1. And it's typical notation to designate this as a vector by putting a little arrow on top, or sometimes people bold it. So that's what you see the magnitude. Sometimes you'll see double absolute value signs. Again, it's just called the magnitude. There's a lot of different notations for vectors that you'll learn if you continue to investigate vectors further. Anyway, if we come down here to your worksheet, the first thing it says is how to do the magnitude. Again, it looks like an absolute value sign, but remember we're just going to be doing the Pythagorean theorem. So for v1, it's going to be 3 squared plus 5 squared, which is going to be equal to 4. How you get that is 9 plus 25, which is equal to 30, no. 9 plus 25, I believe, is 34. I don't know. I'm just thinking like 3, 4, 5 triangle. So that's where that comes from. And unit vectors just mean that they have a length of 1, but the same direction as the, I don't know why they're calling it absolute value there, or magnitude there, but that's up to them. So unit vector just means length or magnitude is equal to 1. And so how you do that typically is you write out the vector. This again is for v1. And then you're going to divide it by its magnitude. So here, what did we say this magnitude was again? So 9 plus 25 is 34. Yeah, I don't know why I think it was that. Okay. This is going to be divided by the square root of 34. And that's how you get. And then you can move the magnitude inside. So you can have 3 over the square root of 34 and 5 over the square root of 34. And again here, they're using parentheses to denote vectors. Sometimes you'll see like the triangle side thing. Or sometimes you'll see this other notation where it's saying 3 times 3 times I plus 5 times j. It all means the same thing. They just, the little caret on top typically means unit vector, so length of 1. But that's more just like notation stuff and not super important. it's best to stay consistent with whatever textbook says to do. So again, here for draw and label v1, you can kind of think of it as like a point, as the arrow going from the origin to the point in the parentheses. So for here, for v1, we're going to go from 3 to 5. That's the point in the parentheses, and then we're going to draw the arrow up like that. And again, it can be like with any point. So we could also do, we could also say go from, I don't know, we could do 6 and 5 instead. And again, you get the same vector because it's just been pushed over to the side, but it's technically the same vector. Just typically when I'm drawing it, I tend to start at the origin because I think it's easier. And it's good to note what it is. And I put a little arrow on top so I know it's a vector. Okay, and then for adding vectors, it's very similar to adding points. If you've ever done trying to find the slope, you'll typically be adding the points. So this is the we'll call it the x component and then the y component of the vector. And again here, so for adding vectors, you're going to add the x component and you're going to add the y component separately, and you're going to end up with another vector. So here we're going to have 1 plus 5, comma 6 plus negative 3. And this here is your new vector v1 plus v2. We could simplify this up a little bit and do that. And then subtracting vectors is the exact same thing. I'll do the next one here. So we're going to do v1 minus v2. So we're going to have 1 minus 5, and we're going to have 6 minus negative 3. And this here is going to be v1 minus v2. So we're going to have negative 4 and 9 as our new vector. And when we're drawing the subtraction of vectors, you can start by drawing. So up here we have v1, and I'm just going to come up with a different value for v2 so that you can do it on your own. But let's just put it, I don't know, let's just put it this way. And so remember, you can move vectors side to side. So I can take this vector here and move it up here. And now this new vector here I can draw by going from the end of v1 to the end of v2. I'll call this v2. This is our new vector v1 plus v2. Okay, and then if we're subtracting vectors, we're going to flip one of them. So if we're flipping v2, because you're multiplying it by negative 1, which is really just flipping the sign, or I guess the direction that goes. Is there a rotate on this? Not sure. Okay, I'll just draw a new one. So we're going to draw it up here going the opposite direction. We're going to call that negative v2. And now this new vector that we can draw going from the end of v1 to the tip of negative v2 is going to be what we call v1 minus v2. So that's what's happening geometrically, and you can kind of see that when you perform it algebraically. And that's exactly what part B is asking you to do, is to sketch the exact same way that we did. All right, and then for linear combination of vectors, it sounds like a confusing name, but all it is just the sum of the vectors. You just multiply it by a scalar first. Just like when finding the unit vector, we divide it by the magnitude. You can multiply vectors by scalars or just normal numbers. So for up here, the first one, you're going to start by doing 4 times 1, comma 4 times 7. And then you're going to find that vector, and then you're going to do the exact same thing for the next step. So we're going to do -2 times 5, comma -2 times -3. I believe we're adding these together then. I'm not sure why it keeps getting me like equal signs. I'm not sure if they end up being equal. I have a feeling they do. But you can verify that that is true for yourself. And you can practice some more adding vectors, adding multiples of vectors for the rest of problem 3. Now, problem 4 here is asking about what's called the dot product. So it looks like multiplication, but the dot is typically bigger in size. And the dot product is a version of where you add vectors together. It's very similar. So what you're going to do is multiply the first 2 terms together. So we're going to have -6 times -3. And then we're going to add 4 times 6. And this here is going to be 18 plus 24, which is an equal 42. And when you do the dot product, you should end up getting a nice normal number. It should not be a vector. Okay, and the dot product is also equal to, this is called the law of cosines, I believe. And no, it's not called the law of cosines. It's so you're gonna, what you end up doing, it's an identity that you can Google on your own because the proof is very long and confusing, but you end up doing v1 dot v2, and this is equal to the magnitude of v1 times the magnitude of v2 times cosine of the angle between them. And so you can do the dot product, which we just did in part A, and you can find the magnitudes, which we did a lot of practice at the beginning of this video, and you can divide the dot product by the product of the magnitudes, and they're going to end up with cosine of the angle, and you take the inverse cosine of that angle. So I'll write that out, what that should look like. So sometimes it's called arc cos, or cos to the power of -1, up to you. Then we're going to do the dot product of v1 and v2, which we just did in part A, times the magnitude of v1 times the magnitude of v2, which I'll let you compute, as you probably need more practice doing so. Okay, and then the scalar projection is something that I'm not super confident on, but it's basically, you have 2 vectors, and you want to find the component of this one that we'll call A. You pretty much want to find that vector length right there. So it should be in the same direction as B, just with a different magnitude. And I believe you end up getting the magnitude. Okay, so the scalar projection uses this formula. I'll write out right here. So we're going to want v1 onto v2. So we are going to do v1 dot v2, and then we're going to be dividing all this by the magnitude of v2. and you should get one number, and I believe that's going to be the magnitude of this pink vector right here. But I'll double check on that before taking my word on that part. And then the projection gives you the vector itself, which I believe you multiply by b, but let me check. Alright, for the projection of v1 onto v2, it's going to be the same thing. Again, the proof for these formulas is pretty confusing. If you are more interested in vectors, I highly recommend finding a video of it online yourself to learn about where these formulas come from, as they can be kind of interesting. But I believe that's beyond the scope of this class. Anyway, for the projection of v1 onto v2, we're going to do the same thing we just did, but then we're going to be multiplying it by the unit vector of v1, or of v2, to ensure that it ends up being parallel to v2. So we're going to be multiplying this by v2 over the magnitude of v2. And this way you should get, this gives you, in our little picture, this gives you the pink vector up there, like the whole vector itself, including its length. And I'll let you compute that for the vector specified on your own. Alright. Now to find if something's orthogonal, the dot product is going to end up being 0. That's all it means is v1 dot v2 is equal to 0. And as you probably recall, computing the dot product before, you're just going to multiply the corresponding components. So we can label these here. If it makes it easier, we can call these the pink and the blue. So you're going to do pink, pink, plus blue, blue. And if there's more vectors, as you'll see in part C, you can simply do the same thing again. So we can hold this here, black times black. And you can keep going for an infinite number of components, which is how some super smart people think that there are like multiple dimensions, and how some people can do math in like 50 directions, because you can just keep adding components as much as you want. So that's what orthogonal means. And for these questions, you should get a yes or no answer. Okay, for the angle with the positive x-axis, I would recommend drawing the vector out on like the graph below. Or you can just draw it here. So you're going to have, we can call this here our vector v, and this here is going to be the x-axis. And the angle between it is this one right here. And so since we can assume that this is the origin, you can essentially assume you know this point right here, which is going to be 5, 8, which means that the length here is going to be 5, and the length here is going to be 8. And you can use any trig thing that you would like to find that angle. At least this is what I'd recommend doing. So here we can do arctan of 8 over 5, and that should give you your angle. I mean, you can also, I suppose, say that the x-axis is the same thing as the vector 1, 0. This is also sometimes called I-hat, which you'll see in like a lot of physics or math textbooks. And so you could also do what we did up here. Where is it? Oh yeah, this part right here in part B, where you do the dot product and then you divide it by the magnitude. I personally think it's a little bit more confusing, but that's might be what this textbook wants you to do. And then for writing v in this form, you pretty much are going to take the magnitude of v, which we've practiced how to do. It's going to be the square root, again, of 5 squared plus 8 squared. Just like Pythagorean theorem, you're finding the length of this arrow up here, the side on the triangle. And then you're just going to do times cosine or sine of the angle that you find in part A. Here it's being confusing. This should really, pretty sure, be v, magnitude of v, times sine of theta. And remember, these mean the magnitude and not the absolute value. That is something that's easy to forget. And this notation is technically called polar coordinates, which is again something that you'll see a lot if you take any further math or physics classes. And Desmos has a polar coordinate version where that will have the magnitude, or they'll times the angle, and like that's another way of graphing. Okay, part number 7 here looks to be more of practicing scalar and scalar projections and regular projections. This we've already gone over up here using this formula right here, where we have the dot product divided by the magnitude of the onto vector, and that gives you the scalar projection. And then you can multiply that scalar projection by the unit vector version of the vector you're projecting it onto. So I recommend using that formula for part A up here. And for parts B, we're going to try and make it look like this picture. So you're going to start by sketching both of the two vectors that it gives you. And then the other vector is going to be the components of the first one here, which up here is A, on top of and parallel to vector B. And that's what it's asking you to do there. And I believe that's all of the questions. If you have anything else, please ask Miss Sue, and she'll probably reach out to me. If you'd like some more applications of vectors, if you take any physics classes, you'll definitely see them a lot, as you'll represent forces as vectors. They can be pretty handy as like they give you the direction that something is pointing rather than just the value. They're also good because they can be a collection of numbers. And so if you do take any computer science classes or get into coding, you have to deal with something called arrays, and you'll see lots of vectors appear there. Lots of like vectors grouped together in matrices, and it'll get very confusing, but it's very interesting. So I believe that's it. Thank you very much for listening, and good luck with any vectors you encounter.